Alright guys, I hope that you're doing really well. In these videos, I'm going to be talking about chapter 19, which deals with electrochemistry. And to begin with, I have put together a list of chapter goals. Each of the goals has to do with a specific section of the book. Notice that I have two of them that are grayed out. We will not be covering those two sections, so I do actually encourage you, if you're interested in looking at section 19.8, which talks about the real world applications of the chemistry that we're going to be discussing, which is going to be in the development of voltaic cells for batteries, fuel cells, and corrosion applications. All right. So electrochemistry is basically looking at the interplay in between chemical and electrical energy, meaning how can we utilize spontaneous chemical reactions in order to give us electricity that we can then utilize to drive an electronic device, or alternatively, how can we use electrical current to drive a non-spontaneous reaction to occur. So as a reaction that would not normally happen, how can we force it to occur by us applying energy in the form of electricity? And we will be talking about both of these cases in a little bit. But to begin with, we usually begin with a review over redox reactions. And this is something that you learned in General Chemistry 1 for the most part. So you might remember about oxidation numbers or oxidation states. They are basically the way that we use in order to account for the electrons that are transferred in any of these redox reactions. In these reactions, we always have one reactant that is going to be gaining electrons, another reactant that is going to be losing electrons, and using the oxidation numbers, it is how we can track which one is gaining and which one is losing. The definition of an oxidation state or oxidation number is that it is the charge that an element would have if the bonding in the compound was 100% ionic. So you don't need to worry too much about this. Now, what you do need to know is going to be the rules for assigning the oxidation numbers, and these are listed on the next slide. All right, so this is the way that I normally teach the oxidation numbers. It's basically one table that contains all of the rules. We're going to go over them and then we're going to apply them into a number of examples. So the rule begins by looking at elements that are in the elemental form in the reaction. For example, the reaction might have hydrogen or oxygen or sodium or aluminum by themselves with no other element attached to them. Also, those elements would have to be in their neutral form, their normal elemental form. So if you find an element in a reaction that is in its elemental form, its oxidation number is going to be equal to zero. So again, for example, if in the reaction you see something like H2 or something like O2 or something like aluminum in the solid form for this guy, these two would be in the gaseous form because that's their elemental form. Then all of those would have an oxidation number of 0, each of them independently. These are not together, they're independently, and you would find them in that way in the reaction. Again, notice that these have no charge, meaning that they are in the elemental, not their ionic form. The ionic form would fall onto the ion rule. So for ions, we have one rule for monoatomic cations. Cation is a positively charged ion. Monoatomic means that it has only one atom. For example, something like Na+. So for all of these monatomic cations, the oxidation number is going to be equal to the ionic charge. So for example, here in my sodium example, the charge is +1, and therefore the oxidation number would also be +1. Now, I'll go ahead and mention something. Let's say that I had found that sodium as part of a compound, NaCl. In that ionic compound, sodium ion is still a monoatomic cation, so it would still have a charge of +1, and it would therefore still have an oxidation number of +1. Similarly, if I had calcium, calcium could be either by itself as Ca2+, or it could have calcium as a compound, something like calcium chloride, CaCl2. In both cases, the calcium ions would take the oxidation number of +2. All right, the next rule for ions is that for a polyatomic ion, meaning an ion that has more than one atom, for example, sulfate or carbonate, then the sum of the oxidation numbers of all of the atoms in that ion needs to equal the charge of the ion. So for example, for sulfate, the sum of the oxidation numbers of the sulfur and the 4 oxygens would have to equal to the charge of the ion, which is -2. And we'll do an example of this in the next page. The next rules are for oxygen and hydrogen. So oxygen, 99% of the times, is going to have an oxidation number of -2. The only exception is if that oxygen is part of a peroxide, for example, hydrogen peroxide, in which case that oxygen is going to take an oxidation number of -1. I'll go ahead and say that in this class, the only peroxide that you might encounter would be H2O2. And so you don't need to worry about being able to recognize any other peroxides because you have not been taught that just yet. So you would say that 99% of the times, the oxygen is going to have an oxidation of -2, unless it is in this form, in which case is -1. Now, hydrogen could be either +1 or -1, depending on what it is bound to. If it is bound to nonmetals, which are typically going to be negative in their oxidation number, then that hydrogen is going to take a +1 oxidation number. On the other hand, if it's bonded to metals, then it's going to have an oxidation number of -1. Next, for group 7 elements, so for fluorine, fluorine is always going to have an oxidation number of -1. On the other hand, the rest of the halogens from that group are going to have typically a charge of -1, but it really depends on what they're bound with. And so what I typically tell you guys is to not remember any rules for the rest of the halogens. Just remember that fluorine is -1. We should be able to figure out the oxidation number of the other halogen by doing some accounting, some calculations, as I will show you in the next page, depending on what they're bound to. The last rule, which is really important, is that if you have a compound, a neutral compound, then the sum of the oxidation numbers needs to be equal to 0, because the charge of that neutral compound is equal to 0. So all of the oxidation numbers for all of the atoms in that compound are going to add up to 0. All right, let's go ahead and apply those rules now to a number of examples. So let's go one by one. And let me show you the way that I do it using the first example. So the way that I do it is that I write my compound here, NiO2, and then I usually do a table. And this is something that I do when I'm starting to teach or to learn how to do this. Later on, you should be able to do this in your head. So I break down the compound into the elements that it's made out of. In this particular case is NiO2, which is a neutral compound. So remember that the last rule said that the sum of the oxidation numbers of that compound need to add up to 0 because the charge is equal to 0. I'm going to be doing all of my accounting here at the bottom. So I'm going to say that the oxidation numbers of these things together have to add up to 0. All right. Then what I do is that I start applying the rules that I discussed in the previous page. One of the rules that we had was for oxygen. We said that oxygen was going to have an oxidation number of -2, 99.9% of the times, unless it was in the form of hydrogen peroxide. Now, so that means that we have already set the oxidation number for that oxygen. And I'll go ahead and put a label here that says up here, this is where I have my oxidation numbers. On the bottom, I have only my accounting. All right, now since I have 2 of those oxygens, that means that I have to account for a total of -4. Basically, -2 times 2 is equal to -4. For nickel here, I kind of have a rule, but let's just say for right now that I'm going to call it x, since it's the only thing that I don't know. So what I do is x minus 4 is equal to 0, therefore x is going to be equal to +4, and that basically becomes the oxidation number for that nickel. In this particular case, we could have also figured out the oxidation number for nickel by thinking about the charge that that nickel was taking, but it might be a little bit difficult for you to see because the oxidation number of oxygen is 2. There is an implicit 2 right here, but since that 2 got reduced to a 1, it meant that the charge of the nickel had been a 4. So that's why it's a little bit harder to do than just doing this. Let's go ahead and do the next one. So I'm going to do SF4, sulfur tetrafluoride. I'm going to divide it into the two elements. It's a neutral compound, so the sum has to add up to be equal to 0. For fluorine, I have a rule. I know that the oxidation number is -1 according to the previous page, but I have 4 of them, so I have to account for -4. And then for sulfur, I don't have any rules, so I'm going to go ahead and call it X. And so X minus 4 is equal to 0. Therefore, again, X is equal to +4, which is the oxidation number for sulfur. Again, the numbers up here are the oxidation numbers. The numbers down here are just for my accounting purposes. So in sapling or in an exam, when I ask you for the oxidation numbers, these are the numbers that I want, the ones that are up here. And in sapling, you're not going to be putting them like this in a circle. You would either be like clicking on a box to select the right number, or you might have to put them like click on the atom and put a number on top of the atom. All right, let's do the next example. So CO is carbon monoxide, CO. That one is going to be pretty simple because I know that oxygen has an oxidation number of -2. And since they are in a ratio of 1 to 1, the only way for this to be equal to 0 would be if the carbon had an oxidation number of +2, and we don't even need a table for that. Done. The next one might be a little bit more complicated. So we're going to have Na2, C2, and O4. And again, I'm going to break it into the components, each of the elements. This is a neutral compound, so the sum is going to add up to be equal to 0. I then can utilize my rule for oxygen, which said that oxygen is going to have a -2 oxidation number, but since I have 4 of them, I have to account for a total of -8. Then what other rule can I use? Well, I don't really have any rules for carbon, but I do have a rule for positive ions, cations, in either by themselves or in the form of a compound, right? And in this case, sodium ions are +1 cations, right? They have a charge of +1. So I know that for those cations, the charge is going to be equal to the oxidation number. The charge of sodium ion is +1 because sodium is on group number 1, so that's where this number comes from. Now I have 2 of them, so I have to account for a total of +2. Now for the carbons, I don't have any rules, so I'm going to call them X, but for each of the carbons is going to be X, but I have 2 of them, so I'm going to call this 2X. And so my equation ends up saying 2 plus 2X minus 8 is equal to 0. Then I'm going to say, okay, 2x minus 6 is equal to 0. Therefore, 2x is equal to 6. And then I'm going to divide both sides by 3. So x is going to be equal to 3. And you have just figured out the oxidation number for each of the carbons. Again, the numbers up here, these are the ones that you need. It's 1 number for each of the elements. So 1 for each of the sodium, +3 for each of the carbons, -2 for each of the oxygens. Those are the oxidation numbers. All right, the next one is hydrogen peroxide, H2O2. Let me start moving a little bit down, make some more room. So H2O2, we can do the same accounting. The oxygen is at, let's see. Did I just call it hydrogen peroxide? Yes, H2O2. This is the one case where your oxygen is going to have a -1 oxidation number. So -1 times 2 gives us a total of -2 here. This is a neutral compound, so it has to add up to 0. This is my unknown, and in this case, I can actually solve it in 2 different ways. One of the ways is to go ahead and call this 2x, and so I have 2x minus 2 is equal to 0, or 2x is equal to +2, or x is equal to +1 by dividing both of them by 2, right? Or we could also figure out by the rules for hydrogen. So the rules for hydrogen are that hydrogen is going to be +1 when it's bonded to a non-metal like oxygen, or it's going to be -1 if it's bonded to metals, right? So we're done with that. The next example is the potassium permanganate. We can do that one in two different ways. One of the ways, let's go ahead and just do it this way by the same exact way. So KMN, oops, that's not an N, KMNO, come on, please. Write what I want you to write, O4. Okay, we're going to do the same exact thing. So we're going to divide it as such. It is a whole compound, so it's going to have to add up to 0. I then use my rule for oxygen, which is that the oxidation number is -2 times 4, that's a -8. I then am going to use the rule for my monoatomic cation in this compound, which is that the oxidation number is going to be equal to its charge. The charge of a potassium ion is a +1. So that's that. And since there's only one of them, that means that I have a +1 right here. Then for manganese, I don't actually have a rule, so I'm going to call it X. And so in this particular case, I have 1 plus X minus 8 is equal to 0, or X minus 7 is equal to 0, or X is equal to +7. And so we are done. Next example, P4O6. All right, P4 tetraphosphorus hexoxide. Same scenario. It's a compound, it adds up to 0, -2 here, therefore -12 here. In this case, I have 4 unknowns, 4 x's. So I have 4x minus 12 is equal to 0, or 4x is equal to 12. Therefore, x is equal to 12 divided by 4, which is equal to 3. And we are done. So +3 for each of the phosphorus. All right, next we go to the most difficult one that I could come up with, that ammonium hydrogen phosphate. So this one would be really difficult for us to do with the same method that we just did. What I would recommend that you do when you have a large ionic compound that has kind of two difficult parts is that you separate them into each of the ions. So in this case, my ammonium, let me go ahead and just put it down here. I'm going to rewrite the compound, which is NH4 2 hydrogen HPO4. Okay. This one, we're going to be dividing it into the two ions that it is made out of. The first ion is the ammonium ion, NH4+. The second ion that is made out of is the hydrogen phosphate. And the charge of that hydrogen phosphate is actually equal to -2. That 2 right here belongs to the charge of this guy. Don't forget your charges. All right, now I can deal with each of the ions independently. And so let me just go back up here and remind you something. Notice that we had a rule for polyatomic ions. For a polyatomic ion, the sum of the oxidation numbers needs to be equal to the charge of the ion. So this is the rule that we're going to use. We're no longer going to put it equal to 0 because we're not dealing with the whole compound. We're going to be dealing with the ions independently. And the other thing that I want to point out is that notice that even though we had 2 of those ammonium ions, it doesn't matter. I'm just going to deal with one ion at a time because the oxidation numbers don't change if you have 2 or 3 or 4 of those ions. The oxidation number for each of the elements within that polyatomic ion is still going to be the same. So this simplifies things a little bit. All right, so how do I deal with my ions? I'm going to rewrite it down here, if you don't mind. I'm going to put the NH4, I'm going to put my table, and I'm going to remember that the sum has to be equal to the charge. So the charge is +1. I then think about, okay, how do I do this? I don't have any rules for nitrogen, but I do have a rule for hydrogen when it's bonded to nonmetals. We know that the hydrogen, when it's bonded to a nonmetal, is going to have a charge of +1. Here we go. +1 times 4 gives us +4, and then the nitrogen would be our x. So what we have is x plus 4 is equal to 1, or x is equal to 1 minus 4, or x is equal to -3. On the other hand, here for my hydrogen phosphate, I'm going to do it on the side here. So I'm going to put H, I'm going to put my P and my O4, and I'm going to split them up into my table, and I'm going to set that equal to -2 because the charge was a -2. I can then use my rule for oxygen. -2 times 4 is -8. Then I think about the rest of the rules. So hydrogen here is bonded to non-metals again, which means that it's going to take an oxidation number of +1. And I only have one of them, so that's a 1. For phosphorus, I don't have any rules, so I'm just going to call it X. So what I have is that 1 plus X minus 8 is equal to -2, or X minus 7 is equal to -2, or X is equal to -2 plus 7, which means that X ended up being equal to 5. And now we are done. So 5 here, +5, and I forgot to put that this -3 goes up here, -3. There we go. And then we had 2 more examples. I'm going to let you guys do this one on your own, and I will go ahead and do this other one. So this one right here, notice that it has sodium and then it has non-metals. So this is an ionic one as well. And we could do it in either of the 2 ways, where we separate the ions or where we don't. In this case, I'm going to do it without separating the ions. So I'm going to take my Na2 and my S2 and my O3 and put my table. I know that oxygen is -2 times 3, that's a -6. I know that this whole thing has to add up to 0. I know that sodium is the cation, which has a charge of +1. And so +1 times 2, that gives me a 2. And then I know that for sulfur, this is going to be 2x. So what we have is that 2 plus 2x minus 6 is equal to 0. Or we could say 2x minus 4 is equal to 0. Or 2x is equal to 4. Or x is equal to 4 divided by 2, which is equal to 2. And with that, I can go and put my +2 right here, and we are finished. All right. So from here, where do we go? The next thing is that you need to remember what a redox reaction is and what reduction and oxidation is. So a redox reaction is a reaction where you're going to have electron transfer. In that redox reaction, one of the components, one of the reactants is going to be reduced, where reduced means that it's going to be gaining electrons. And one of the other reactants is going to be oxidized, where oxidation means that it's going to be losing electrons. Both reduction and oxidation are going to occur together. And you might have learned oxidation and reduction by either of these 2 sayings. This one says Leo says Ger, or loss of electrons is oxidation, gain of electrons is reduction. This is my favorite one because it reminds you that what you're losing and what you're gaining is electrons. On the other hand, this one, oil rig, tells you that oxidation is losing and reduction is gaining. And the only problem with this one is that it doesn't remind you what it is that you're losing or gaining. Now, another way to remember oxidation and reduction is that oxidation is going to be an increase in the oxidation number, while reduction is going to be a decrease in the oxidation number. And the reason I like this one as well is because it reminds you that reduction is going to decrease the oxidation number. But for the most part, I recommend this one. It's kind of easy to remember that the lion says Ger or Leo says Ger. All right. So another thing that you should have learned in General Chemistry 1 was how to identify oxidation and reduction agents. So as I mentioned, one of your reactants is going to be oxidizing and one of your reactants is going to be reducing in the reaction, right? So the oxidation agent is the reactant that acts on the other reactant to oxidize it. In the process of doing that, it itself gets reduced. And examples of oxidizing agents are shown here. You do not need to remember them at all. Now, reducing agents act on the other reactant in order to reduce them. And in doing so, in that same process, they get oxidized themselves. So notice that the oxidizing agent is the agent that gets reduced, while the reducing agent is the agent that gets oxidized. So what we're going to be doing is that we're going to be looking at redox reactions. In those redox reactions, we're going to see what atoms are gaining electrons, what atoms are losing electrons as they go from reactants to products. Those that lost electrons got oxidized, and therefore they are those that lost electrons got oxidized, which means that they are the reducing agents, and those that gained electrons got reduced, and those are going to be the oxidizing agents. So let's go ahead and do an example here. All right, so in the following balanced redox reaction, what species is being oxidized? So oxidized means that we're going to be losing electron. Which one? Lost electrons. And so what we're going to do is that we're going to be looking at each of the elements on the reactants, looking at the oxidation number on the left side, and then looking at the oxidation number on the right side to see if they changed. I would recommend that you always begin at looking at the things that are in the ionic form because it's kind of easy to see. For example, I can look at my hydrogen here, and since it is a cation, monoatomic cation, that means that its oxidation number is +1. And so then I can look at the other side, look for that hydrogen, and in this case, since the oxygen is a -2, -2, -2 equal to 0, that means that these hydrogens are going to have to be +1. And again, you can do it by doing the math here. So 2x minus 2 equal to 0, or 2x is equal to +2, or x is equal to 2 divided by 2, which is equal to 1. Or you can just think about the fact that hydrogen is bonded to a non-metal, and therefore it is +1, right? So in this case, hydrogen did not change. It went from +1 to +1. So then I encourage you guys to go ahead and look at the remaining 3 elements, manganese, oxygen, and iron, and see which one lost electrons. And at the same time, answer this, but at the same time, look at which one got reduced, please. Go ahead and pause the video, give it a try. All right, guys, so the way that I did it, I went ahead and looked at everything possible. But the next thing that was easiest for me to look at was my iron. Notice that I have iron as a +2, charge of +2, which means that its oxidation number is +2. I also have iron here as a +3. That means that it changed. And so I want to write down and see, did it gain or did it lose electrons? The way that I usually do it is that I just write it here. Fe went from 2+ to an Fe of 3+. Okay, and so going from a 2+ to a 3+, it means that it got less negative. It actually lost electrons to become more positive, right? So if it lost electrons, that means that it got what? Did it get oxidized or did it get reduced? If it lost electrons, it got oxidized. And so that answers the question that we were looking for, right? So what got oxidized was our iron 2+. All right, just to continue looking at the rest, I'm going to then look at my manganese. On the right-hand side, I already know that manganese has a 2+ oxidation number, but what about on the left? Well, I can do my accounting again. I can say, okay, -2 for the oxygen. I have 4 of them, so that's a -8. My manganese is X, and then this is going to have to add up to a charge, which is a charge of -1. And so the sum of this has to be equal to the charge of the ion. This is the permanganate ion. And so therefore my X is going to be equal to +7. So on the left-hand side, my manganese was +7. On the right-hand side, it is a +2, so it definitely changed. So manganese went from +7 to, on the other side, being manganese as a +2. That means that it ended up changing, obviously. It means that it actually got more negative. It means that it gained electrons because each of the electrons is negative. And if it gained electrons, that means that it got reduced. All right. So we are done with this part. Now, on the next page, I'm actually going to ask you for the same exact system, which one is the oxidizing agent and which one is the reducing agent. So let's go ahead and do it here since we have all the information that we need. All right, so the atom that got oxidized, that means that that one is the reducing agent, right? The one that got oxidized is the reducing agent. And the reason for that is that it enabled the other atom to get reduced. So that makes it the reducing agent. On the other hand, the manganese plus 7, which got reduced, would be the oxidizing agent because it enabled the iron to be oxidized. And that right there is that. Okay. Before I move from here, there's a couple of things that I wanted to say. One of the things is that you're always going to be looking at the reactants, the things on the left-hand side of the arrow, in order to select the oxidizing agent or the reducing agent. So oxidizing agent and reducing agent is going to be your reactants, right? Even though I wrote everything here on the right-hand side, I'm really talking about the iron 2 plus and the manganese plus 7, which are my reactants, this guy and this guy. Those are the ones that got oxidized. Those are the ones that got reduced. Those are the ones that were the reducing agent. Those are the ones that were the oxidizing agent. The only reason why I wrote this here is just to show you the change. And the other thing that I wanted to tell you is that how is it that you figure out if you lost electrons or gained electrons? Well, you have to remember that electrons are negatively charged. So if you had gained an electron, it would take the 2 plus and make it less positive, right? It would go from a 2 plus to a 1 plus. But in this particular case, you went to a 3 plus, so that means that you lost electrons, right? Similarly here, you went from a plus 7 to a plus 2. That means that it became more negative, and that means that it gained electrons. All right. When looking at redox reactions, we can separate them into two half reactions, one that explains what's the oxidation process and one that explains what is the reduction process. For example, here we have 2 aluminum, this is aluminum metal in the solid form, non-ionic, plus 2 chlorines, these are chlorine gases, again non-ionic, this is the elemental forms, and these are forming 2 aluminum chloride, which is an ionic compound. In this case, in the right hand side, the aluminum carries a charge of 3 plus and the chloride carries a charge of negative 1 because this is an ionic compound. All right, I can separate it into the oxidation and the reduction. And initially, I don't know which one is oxidation and which one is reduction. So what I'm going to do is that I'm going to take my first element and put it and separate it here. And then I know that that aluminum is going to aluminum 3 plus on the right hand side because again, this is the ionic compound where the aluminum carries a charge of positive 3. And I put that here. So aluminum went to aluminum 3 plus. I then think about I need to balance this equation in terms of the charges. Notice that on the left-hand side, I have a charge of 0, and on the right-hand side, I have a charge of positive 3. So to make it even, what I need to do is to add 3 electrons on that right-hand side. Now, this equation, as written, having the electrons on the right-hand side, it means that we are losing electrons because our product is electrons, right? We are liberating electrons as part of the product. So that means that since we are losing electrons, that becomes our oxidation reaction. Now the other part of the reaction is taking our chlorine Cl2, again, a non-ionic elemental form, and then we're converting it into chloride ions. These are Cl minus with a -1 charge, because again, this is an ionic compound. And so I just go and write Cl2 goes to Cl minus. All right, notice that in order for this equation to balance, I need to have a coefficient of 2 here, otherwise I would have the wrong number of chlorines in general on the left and on the right. Now I have to still balance the charge. So on the right hand side, I have a -2 charge because each of the chloride is -1. And so I need to add electrons, and those electrons would have to be added on the left hand side to make both sides have a 2 charge, right? And so that's where this equation comes from. Now, since the electrons are being added on the reactant side, that means that the chlorine is gaining electrons to become chloride, and so that means that this is a reduction, okay? All right, let's go ahead and do examples. So first example is to separate the following redox reaction into half reactions. What we have is rubidium fluoride going to 2 rubidiums and fluorine gas, I should say. All right, in this case, the left-hand side contains an ionic compound, and rubidium, go ahead and find it on the periodic table. It is number 27, I believe, 37, sorry. And it is in group number 1, which means that rubidium has a charge of +1. So I'm going to write it in this case, my rubidium, +1. And on the right-hand side, it is going to rubidium by itself, just Rb. I have the right number on both left and right? And then from there, I need to look at the charges. This side has a charge of +1. The right-hand side has no charge. And so to make them equal, all I can do is to add electrons. To make them equal, in this case, I would have to add 1 electron here so that positive and negative cancel out to become equal to 0. Now, since the electrons are on the left-hand side, that means that we are gaining electrons, and that means that this is a, let's see, gaining electrons is a reduction. Awesome. Notice also that the oxidation number of the rubidium is decreasing, right? That's why it is a reduction. It went from a +1 to a 0. Now, similarly, I'm going to look at my fluoride ion. In this case, it's part of an ionic compound, so it's beginning as fluoride, which has a -1 charge because it's a halogen from group 7. And then on the right-hand side, I have my fluorine as F2. That one has a charge of 0. Now, in order to balance them, I first have to look at the number of fluorines. I have 2 here. That means that I need a 2 right here. And then the next thing is I need electrons. So do I put the electrons on the left or on the right-hand side to make it even? On the left, I have a -2 charge. If I add electrons here, it would become more negative. So it would not be the same as the right-hand side. So I have to add the electrons here, and it would be a total of 2. Oops, that's not a 2. 2, thank you, electrons to make it -2 on both sides. Now, since the electrons are on the product side, that means that this is a oxidation. We are losing electrons. That's not how you spell oxidation. Here we go. Oxidation. All right. I also recommend that you guys look at example 19.1 and practice problem 19.1, which shows you how to separate redox processes into half reactions.